Close your eyes and imagine the most violent, energetic phenomenon in the universe. Not a supernova, though they're spectacular. Not a gamma-ray burst, though they're devastating. The title of most dangerous cosmic object belongs to quasars, objects so luminous they outshine entire galaxies, so energetic they could sterilize worlds across vast distances, so extreme they challenge our understanding of physics. Quasars are among the universe's greatest mysteries and most terrifying realities. For decades after their discovery in the 1960s, astronomers couldn't explain what they were: distant star-like objects emitting more energy than seems physically possible. Today we know the truth. Quasars are supermassive black holes actively feeding, converting matter into energy with terrifying efficiency, unleashing radiation that makes our sun look like a candle next to a searchlight. Tonight, we'll explore these cosmic monsters. We'll discover what quasars are: active galactic nuclei powered by black holes millions to billions of times the sun's mass. We'll learn how they form when galaxies collide and matter spirals into central black holes. We'll examine the unimaginable energies involved: single quasars outshining hundreds of billions of stars. And we'll confront a disturbing question: how dangerous are quasars to humanity? Could a quasar's radiation reach across space to threaten Earth? This is the story of the universe's most extreme objects, nature's ultimate engines of destruction and creation, reminders that space harbors phenomena far more dangerous than we ever imagined. The story of quasars begins with a mystery. In the early 1960s, radio astronomers detected strange sources in the sky, powerful radio emissions coming from what appeared to be faint, star-like points of light. These weren't stars. Their properties were all wrong. They were called quasi-stellar radio sources, shortened to quasars. The first quasar, 3C273, was identified in 1963 by astronomer Martin Schmidt. Using the 200-inch Hale telescope at Mount Palomar, Schmidt obtained a spectrum of this mysterious object. What he saw shocked him. The spectral line's fingerprints of chemical elements were shifted dramatically toward the red end of the spectrum, indicating enormous velocity. Applying Hubble's law, which relates redshift to distance, Schmidt calculated that 3C273 was over 2 billion light-years away, far beyond our Milky Way, residing in the distant universe. This was staggering. If 3C273 was that far away yet still visible with telescopes, it had to be incredibly luminous, thousands of times brighter than entire galaxies, containing hundreds of billions of stars. How could a point-like object outshine billions of stars? The numbers seemed impossible. 3C273 was emitting as much energy as 1 trillion suns. Astronomers struggled to explain what kind of object could produce such staggering luminosity from such a compact region. More quasars were discovered rapidly. Each was extraordinarily distant and luminous. Observations revealed that quasars varied in brightness over days, weeks, or months. This variability constraint was crucial. If an object varies in brightness over a certain timescale, its size cannot be larger than the distance light travels during that time. Otherwise, different parts of the object couldn't coordinate changes. If a quasar brightens in a week, its energy-emitting region must be less than 1 light-week across about 180 billion miles, or roughly 20 times the size of our solar system. This is tiny compared to galaxies, which are hundreds of thousands of light-years across. How could something smaller than our solar system outshine an entire galaxy? The question haunted astronomers. Early theories were exotic. Perhaps quasars were white holes, hypothetical opposites of black holes, spewing matter and energy. Perhaps they were the cause of exploding galaxies. Perhaps they weren't as distant as redshift suggested, evading Hubble's law through some unknown mechanism. None of these explanations held up. The breakthrough came from understanding black holes. By the late 1960s and early 1970s, theoretical work on black holes' regions of space-time, where gravity is so strong that nothing can escape, had matured. Astronomers realized that black holes weren't just cosmic curiosities but could be powerful energy sources. When matter falls into a black hole, it doesn't just disappear, it spirals inward, forming an accretion disk, a swirling disk of gas and dust, heated to millions of degrees by friction and gravitational compression. This disk radiates enormous energy across the electromagnetic spectrum: visible light, ultraviolet, X-rays. The process converts mass into energy with efficiency far exceeding nuclear fusion. Einstein's E equals mc squared shows that mass-energy conversion is incredibly potent. Accretion onto black holes converts up to 10–40% of infalling mass into radiated energy, compared to nuclear fusion's to 0.7%. This makes accreting black holes the universe's most efficient energy sources. But not just any black hole could power a quasar. The black holes at quasar centers are supermassive, millions to billions of times the Sun's mass. When such a black hole actively feeds on surrounding gas, funneling in thousands of solar masses of material over millions of years, it releases unimaginable power, creating a quasar. By the 1980s, consensus emerged. Quasars are active galactic nuclei, AGN, the luminous cores of distant galaxies, where supermassive black holes are actively accreting matter. The term quasar became shorthand for the most luminous AGN, typically found in the early universe. But why are quasars so distant? Why don't we see them nearby? The answer lies in cosmic evolution. Quasars were most common when the universe was young, 1 to 3 billion years after the Big Bang. Back then, galaxies were smaller, gas-rich, and frequently colliding, feeding central black holes prodigiously. As the universe aged, galaxies settled down, gas was consumed or expelled, and quasar activity declined. Today, quasars are rare. Nearby galaxies host supermassive black holes, including our Milky Way, but most are dormant or feeding only gently, not producing quasar-level luminosity. The most distant quasars observed lie over 13 billion light-years away, their light traveling most of the universe's history to reach us. We see them as they were when the universe was less than 1 billion years old. Studying these ancient quasars reveals the universe's early conditions and how the first supermassive black holes formed, a question that still puzzles astronomers. Quasars opened a window into the universe's youth and extremes. They showed that black holes aren't just theoretical oddities, but real powerful actors in cosmic evolution, shaping galaxies and perhaps regulating star formation across cosmic time. And they revealed that the universe contains phenomena far more energetic and dangerous than anyone had imagined. To understand quasars, we must dissect their structure, examining each component and how they work together to create the universe's most luminous objects. At the heart of every quasar lies a supermassive black hole, a black hole with mass ranging from millions to tens of billions of solar masses. These aren't stellar mass black holes formed from collapsing stars. They're monsters that likely grew over billions of years through accretion and mergers. The central black hole itself is invisible, defined by its event horizon, the boundary beyond which nothing can escape. For a supermassive black hole of 1 billion solar masses, the event horizon has a radius of about 3 billion kilometers, roughly 20 times the distance from the Sun to Earth, or about 0.02 light-years. Surrounding the black hole is the accretion disk, a flattened, rotating disk of gas and dust spiraling inward. Material in the disk doesn't fall straight in. Angular momentum forces it into orbit, gradually spiraling closer as friction and magnetic fields transfer angular momentum outward. As gas spirals inward, gravitational potential energy converts into kinetic energy and then into heat through friction. Inner regions of the disk, closest to the black hole, are hottest, reaching millions of degrees Kelvin, and emit X-rays and ultraviolet light. Outer regions are cooler and emit visible and infrared light. The accretion disk is where most of the quasar's luminosity originates. The disk can extend from just outside the event horizon to light years away, though most luminosity comes from the innermost regions. The disk's structure is complex, governed by magnetohydrodynamics, the interplay of magnetic fields, gas dynamics, and gravity. Turbulence in the disk, driven by the magnetorotational instability, generates friction that heats the gas and allows angular momentum transport. The amount of energy radiated depends on the accretion rate, how much mass falls into the black hole per unit time. If a quasar accretes 1 solar mass of material per year and converts 10% of that mass to energy via E equals mc squared, it produces about 10 to the power of 45 ergs per second, roughly 10 trillion times the Sun's luminosity. The brightest quasars have luminosities exceeding 10 to the power of 47 ergs per second, equivalent to hundreds of trillions of suns. This accretion process has a limit. The Eddington limit describes the maximum luminosity a black hole can sustain through accretion. As the black hole accretes and radiates, radiation pressure pushes outward on infalling gas. If luminosity exceeds the Eddington limit, radiation pressure overcomes gravity, halting further accretion. For a supermassive black hole, the Eddington luminosity is roughly 10 to the power of 46 ergs per second per billion solar masses. Some quasars radiate near the Eddington limit, suggesting they're accreting at maximum sustainable rates. Surrounding the accretion disk is the broadline region, BLR clouds, of gas moving at thousands of kilometers per second, orbiting the black hole at distances of light days to light months. These clouds are illuminated by the intense radiation from the accretion disk, causing them to emit spectral lines, particularly hydrogen lines like H-alpha. The gas moves so fast that Doppler broadening smears these lines across the spectrum, creating broad emission features that characterize quasar spectra. Farther out, typically hundreds to thousands of light-years from the central black hole, lies the narrow line region, NLR, gas moving more slowly, producing narrower spectral lines. This gas is also photoionized by the quasar's radiation but moves at lower velocities due to its greater distance. Obscuring the central regions in some viewing angles is the dusty torus, a donut-shaped structure of gas and dust surrounding the accretion disk and BLR. The torus absorbs radiation from the central engine and re-emits it as infrared. The orientation of the torus relative to our line of sight affects how we observe the quasar. Face-on views show the full blazing core, while edge-on views hide the central regions behind the torus, revealing only the NLR. One of the most dramatic quasar features is the relativistic jet narrow beams of plasma ejected from near the black hole at nearly the speed of light. Not all quasars have jets, but when present, they're spectacular. Jets can extend millions of light-years into space, far beyond the host galaxy, depositing enormous energy into intergalactic space. How jets form is still debated, but involves magnetic fields threading the accretion disk and black hole. The Blandford-Znajek mechanism proposes that magnetic fields extract rotational energy from a spinning black hole, channeling it into jets. Magnetic fields also launch material from the inner accretion disk, accelerating it to relativistic speeds through magnetic pressure. Particles in jets, mostly electrons and protons, are accelerated to extreme energies, emitting radiation across the spectrum via synchrotron radiation and inverse Compton scattering. When a jet points nearly toward Earth, relativistic beaming makes the quasar appear even brighter. Photons are concentrated in the direction of motion, and time dilation makes the jet appear faster and more energetic than it is in its rest frame. Such objects are called blazars, and they're among the universe's most luminous objects. Quasars aren't isolated. They reside at the centers of galaxies. Early observations struggled to see the host galaxy because the quasar outshines it by factors of hundreds. But with advanced techniques blocking the quasar's light, or observing in specific wavelengths, astronomers image quasar host galaxies. They're often large, massive galaxies, sometimes showing signs of disturbance or ongoing mergers, consistent with theories that galaxy interactions trigger quasar activity by funneling gas into central black holes. The quasar structure we've described is called the unified model of AGN. It posits that different types of active galactic nuclei, quasars, Seyfert galaxies, radio galaxies, blazars, are fundamentally the same object seen from different angles and at different stages of activity. Orientation effects and the obscuring torus explain why they appear different. A quasar viewed edge-on, with the torus blocking the central engine, looks like a radio galaxy. A quasar viewed face-on, with jets pointing toward us, becomes a blazar. This unification simplifies understanding and shows that supermassive black hole accretion is a universal phenomenon. Quasars are dynamic. Their luminosity varies on timescales from hours to years, reflecting changes in accretion rate, disk instabilities, or material passing through the jet. This variability allows astronomers to probe the compact regions near the black hole, studying how matter behaves under extreme gravity and magnetism. Understanding quasar anatomy reveals why they're so powerful. It's not magic, it's physics. The enormous gravity of supermassive black holes, the efficiency of accretion, and the interplay of magnetic fields and relativistic effects combine to create nature's ultimate power generators. These structures, though tiny compared to galaxies, dominate their host galaxy's energy output and influence their evolution across cosmic time. Quasars don't exist in isolation, they're products of galaxy evolution. Understanding how quasars form requires examining how supermassive black holes form, how they're fed, and what triggers episodes of intense accretion. Supermassive black holes likely formed in the early universe through several possible pathways. One pathway involves the collapse of massive primordial gas clouds in the universe's first billion years. Before stars enriched the cosmos with heavy elements, pristine hydrogen and helium clouds could collapse into massive objects, perhaps tens of thousands of solar masses, that quickly formed black holes. These seed black holes grew by accreting surrounding gas and merging with other black holes during galaxy mergers. Another pathway involves the remnants of the first generation of stars, POP3 stars, which were massive, hundreds of solar masses, and short-lived. When they exploded as supernovae or collapsed directly into black holes, they left behind black holes of tens to hundreds of solar masses. These seeds grew through continuous accretion over billions of years. A third possibility is direct collapse in rare conditions, gas clouds could collapse directly into intermediate mass black holes of thousands to tens of thousands of solar masses, bypassing star formation entirely. These seeds would then grow to supermassive scales. Evidence suggests that supermassive black holes existed surprisingly early, less than 1 billion years after the Big Bang, requiring rapid growth. Some quasars observed at redshift Z is greater than 7, when the universe was only 700 million years old, host black holes of 1 billion solar masses. Growing a seed black hole from stellar mass to 1 billion solar masses in such short time challenges theories, requiring near-continuous accretion at or above the Eddington limit. This remains an active area of research. Once a supermassive black hole exists at a galaxy's center, it can remain dormant if starved of fuel. The Milky Way's central black hole, Sagittarius A*, has a mass of about 4 million solar masses but accretes only trickles of gas, producing faint emission, not a quasar. For a quasar to ignite, the black hole needs a massive influx of gas, thousands to millions of solar masses funneled into the central region. Galaxy mergers are prime triggers for quasar activity. When two galaxies collide, their gravitational interactions disturb gas distribution, driving shockwaves and losing angular momentum that allows gas to fall inward toward the central black holes. Simulations show that major mergers collisions between galaxies of comparable mass efficiently funnel gas to galactic centers, potentially triggering quasar activity. Observationally, many quasar-host galaxies show signs of recent or ongoing mergers, tidal tails, disturbed morphologies, companion galaxies nearby. The correlation between mergers and quasar activity supports this connection. Though not all quasars are in merging systems, secular processes like bar-driven gas inflows or minor mergers can also feed black holes. Galaxy interactions aren't the only pathway. In gas-rich early galaxies, cold gas streams, rivers of dense gas flowing along cosmic filaments, could feed central black holes directly without requiring mergers. These streams, observed in simulations and inferred from observations, channel material from large scales into galaxy centers, sustaining accretion. Bar instabilities in disk galaxies can also drive gas inward. A galactic bar, an elongated structure of stars and gas, creates gravitational torques that transfer angular momentum, allowing gas to spiral toward the center. This process might explain quasar activity in isolated galaxies. Once gas reaches the central region, it doesn't directly fall into the black hole. Instead, it settles into an accretion disk, gradually spiraling inward as described earlier. The disk's lifetime depends on the fuel supply and accretion rate. If a merger delivers 10 billion solar masses of gas and the black hole accretes at 10 solar masses per year, the quasar phase lasts about 1 billion years. However, accretion is episodic periods of intense feeding followed by quiescence, as gas is exhausted or blown away by the quasar's own radiation and jets. Quasar feedback, the influence of the quasar on its host galaxy, eventually shuts down the quasar itself. The intense radiation and powerful jets heat and expel gas from the galaxy, blowing away the fuel supply. This self-regulation explains why quasars don't shine indefinitely and why central black holes have masses correlated with their host galaxy's properties. The black hole grows until its feedback halts accretion and star formation. The life cycle of a quasar might proceed as follows. A galaxy-rich region of the early universe hosts young galaxies full of gas. Two galaxies collide, disturbing gas and funneling it toward the central black holes. Accretion ignites, and a quasar blazes to life, shining for tens to hundreds of millions of years. The quasar's radiation ionizes surrounding gas, its jets punch through the galaxy, and winds driven by radiation pressure expel gas from the galaxy. Accretion slows, the quasar dims, and the black hole enters quiescence. The galaxy, now depleted of gas, transforms from blue star forming to red and dead, an elliptical galaxy with little ongoing star formation. The black hole sits dormant unless future gas infall or another merger rekindles accretion. This cycle repeats throughout cosmic history, but was most vigorous when the universe was young. Between redshifts Z to 2 to 3, when the universe was 2 to 3 billion years old, quasar activity peaked, corresponding to the era when galaxies were most gas-rich and mergers most frequent. Today, massive galaxies have exhausted most star-forming gas, and mergers are rarer, so quasars are uncommon. Low-level AGN activity persists in many nearby galaxies. Seyfert galaxies, liners. Low luminosity AGN representing lower accretion rates onto supermassive black holes. These aren't quasars in luminosity but represent the same fundamental process operating at reduced intensity. The formation and evolution of quasars intertwine with galaxy evolution. Supermassive black holes grow in tandem with galaxies, fed by processes that also build galactic bulges and regulate star formation. This co-evolution, evidenced by correlations like the M-sigma relation black hole mass correlated with stellar velocity dispersion in the bulge, suggests that black holes and galaxies influence each other profoundly, shaping cosmic structure. Understanding quasar formation illuminates how the universe's structure developed and how the most extreme objects emerged from cosmic evolution's natural progression. Quasars aren't anomalies, they're an inevitable consequence of gravity, gas, and the assembly of structure in an expanding universe. To appreciate why quasars are the universe's most dangerous objects, we must grasp the sheer scale of energy they wield. The numbers are almost incomprehensible, defying everyday experience and intuition. Let's start with our Sun, a typical star and our primary energy source. The Sun's luminosity is about 3.8 times 10 to the power of 33 ergs per second, or roughly 400 trillion watts. This energy, generated by nuclear fusion in the Sun's core, lights and warms Earth, drives weather, and sustains life. Now consider a bright quasar like 3C273, one of the first discovered and one of the closest. Its luminosity is roughly 4 times 10 to the power of 46 ergs per second, about 10 trillion times the Sun's output. To put this in perspective, 3C273 emits as much energy every second as the Sun emits in 300,000 years. The brightest known quasars exceed 10 to the power of 47 ergs per second, 100 trillion times the Sunday. These objects outshine their entire host galaxies, which might contain 100 billion stars. A single quasar, concentrated in a region smaller than our solar system, outputs more light than hundreds of billions of stars combined. Where does this energy come from? Not nuclear fusion. Fusing hydrogen into helium releases about 0.7% of mass as energy. Quasars require something far more efficient: accretion onto a black hole, where matter falling into the intense gravitational field converts gravitational potential energy into radiation. Achieves efficiencies of 10–40% depending on black hole spin and accretion details. This is orders of magnitude more efficient than any other energy source in nature. Consider the mass-energy conversion. If a quasar accretes 10 solar masses per year and converts 10% of that to energy, it releases approximately E equals 0.1 times 10m times c squared. E is approximately equal to 1.8 times 10 to the power of 54 ergs per year. E is approximately equal to 6 times 10 to the power of 46 ergs per second. This is enough energy to vaporize Earth-sized planets instantaneously, to boil away entire atmospheres from hundreds of light years away, to flood entire galactic regions with deadly radiation. Quasars emit across the electromagnetic spectrum radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The spectrum isn't evenly distributed. Much of the power emerges as ultraviolet and X-rays from the hot inner accretion disk. X-ray luminosities can reach 10 to the power of 45 ergs per second or higher, equivalent to a billion suns worth of X-rays. No star produces such intense high-energy radiation. Only accretion onto black holes achieves this. The radiation isn't just intense, it's varied and complex. The accretion disk emits thermal radiation, a blackbody spectrum from the hot gas. The corona, a region of extremely hot, tenuous plasma above the disk, scatters photons to even higher energies through Compton scattering, producing hard X-rays. The broad line region emits strong emission lines. The jet, when present, produces non-thermal radiation from synchrotron emission, electrons spiraling in magnetic fields, and inverse Compton scattering electrons boosting photon energies. This multi-component emission makes quasar spectra rich and complex. Let's discuss jets in more detail. Not all quasars have jets, but when present, they're staggering in scale and power. Jets transport energy and momentum from the black hole's vicinity to intergalactic scales. A typical jet carries 10 to the power of 44, 10 to the power of 45 ergs per second of kinetic power comparable to the luminosity of entire galaxies. Jets can extend for millions of light years, excavating giant cavities in intergalactic medium, depositing energy that heats gas and affects large-scale structure. The speeds involved are dizzying. Material in jets moves at 0, 95 c to 0, 999 c within a few percent of light speed. At these velocities, relativistic effects dominate. Time dilates, lengths contract, and the jet's energy is amplified by Lorentz factors gamma of 10 or more. When a jet points toward Earth, relativistic beaming concentrates radiation in our direction, making the blazar appear extraordinarily bright, sometimes varying in brightness dramatically over hours as blobs of plasma move down the jet at relativistic speeds. Quasars also produce particle radiation cosmic rays. Jets accelerate protons, atomic nuclei, and electrons to ultra-high energies up to 10 to the power of 20 eV or beyond. These cosmic rays travel through intergalactic space, occasionally reaching Earth. The origin of ultra-high energy cosmic rays remains debated, but quasars and other AGN are leading candidates. The mechanical power of jets and winds affects galaxy evolution. Simulations show that quasar-driven outflows, sometimes called quasar mode feedback, can expel gas from galaxies, quenching star formation and transforming blue spiral galaxies into red elliptical galaxies. This feedback regulates black hole growth and galaxy mass, explaining observed correlations. The energy deposition isn't purely destructive. In galaxy clusters, AGN jets inject energy into the intra-cluster medium, preventing catastrophic cooling and regulating star formation. Without this heating, gas would cool and fall into cluster centers, forming stars at unsustainable rates. AGN feedback maintains a balance, ensuring galaxies and clusters evolve in observed ways. Let's quantify danger. Suppose a quasar emitting 10 to the power of 46 ergs per second aims its beam toward Earth. How close would we need to be for serious harm? The flux F received at distance d is F equals L divided by 4πd squared. For ultraviolet and X-ray radiation to deliver lethal doses rapidly, suppose we need a flux of 10 to the power of 10 ergs cm squared s at Earth, an extreme overestimate for lethality but useful for illustration. Then, D equals sqrt_L divided by 4πf. D is approximately equal to sqrt 10 to the power of 46, 4p times 10 to the power of 10. D is approximately equal to 3 times 10 to the power of 17 centimeters, is approximately equal to 100 light-years. So within about 100 light-years of a bright quasar, radiation could be immediately dangerous. At greater distances, danger decreases with the square of distance. Earth, separated from the nearest quasar by billions of light-years, receives negligible flux, 3C273, despite being immensely luminous, appears as a faint 13th magnitude star, invisible to the naked eye. However, proximity isn't the only concern. Quasar radiation can ionize interstellar gas over vast distances, creating enormous ionized bubbles. In the early universe, quasars might have played a role in reionization, ionizing neutral hydrogen filling space after the Big Bang's recombination era. Each quasar could ionize a region tens of millions of light-years across, fundamentally altering the universe's state. For any planet in a quasar's host galaxy, the situation is dire. The quasar's radiation floods the galaxy, ionizing gas, destroying molecular clouds where stars form, and likely stripping atmospheres from planets within the inner kiloparsecs. Life, if it exists, faces sterilizing radiation. Only planets far from the galactic center, shielded by dust and gas, might survive. Quasars also produce gravitational waves during black hole mergers. When two galaxies hosting supermassive black holes merge, their black holes eventually spiral together and merge, releasing enormous energy in gravitational waves. The LIGO and Virgo detectors observe stellar mass black hole mergers. Future space-based detectors like LISA will detect supermassive black hole mergers, each event emitting 10 to the power of 59 ergs or more in gravitational wave energy, more than the Sun will emit in its entire lifetime, over timescales of hours to days. In summary, quasars wield energy on scales that dwarf nearly every other phenomenon. Only the Big Bang itself, and perhaps certain exotic events like gamma-ray bursts, compare. This energy, concentrated and directed, makes quasars instruments of both creation, triggering star formation through shocks, enriching intergalactic space with elements and destruction, reshaping galaxies, quenching star formation, and rendering vast regions hostile to life. Having established quasars' immense power, let's confront a crucial question. How dangerous are quasars to life, specifically to humanity and Earth? Should we fear quasars, or are they distant enough to be harmless? First, consider distance. The nearest known quasar, Markarian 231, lies about 600 million light-years away. Most quasars are billions of light-years distant. At such distances, the inverse square law dramatically dilutes radiation. Even the brightest quasar, emitting 10 to the power of 47 ergs per second, delivers negligible flux at Earth, comparable to a faint star. To quantify, 3C273 at 2.5 billion light-years, with luminosity to 4 times 10 to the power of 46 ergs s, has a flux at Earth of approximately F equals L divided by 4pd squared. F is approximately equal to 4 times 10 to the power of 46, 4p times 2.5 times 10 to the power of 9, Li times 10 to the power of 18 cm, Cs 12. F is approximately equal to 10 to the power of negative 14 ergs, cm squared, S. For comparison, the Sun delivers about 1.4 times 10 to the power of 6 ergs, cm squared orders, at Earth. The quasar's flux is 20 orders of magnitude smaller, utterly negligible. So from currently existing quasars, Earth faces zero danger. We're far too distant for their radiation to affect us. Even if 3C273 suddenly brightened tenfold, we'd barely notice. Distance is our shield. But what if a quasar were closer? Suppose Sagittarius A*, the Milky Way's central black hole, ignited as a quasar. Sagittarius A times has a mass of 4 million solar masses. If it accreted at the Eddington limit, its luminosity would be roughly L-ed is approximately equal to 1.3 times 10 to the power of 38 times mm ergs s. L-ed is approximately equal to 5 times 10 to the power of 44 ergs s. This is 100,000 times the Sun's luminosity and AGN, though not as bright as the most luminous quasars. Earth lies about 26,000 light-years from the galactic center. The flux received would be F is approximately equal to 5 times 10 to the power of 44, 4 pi times 26,000 Ly times 10 to the power of 18 cm, Lie squared. F is approximately equal to 2 times 10 to the power of negative 5 ergs cm squared, S. This is still far less than sunlight. The radiation would increase Earth's sky brightness slightly, but wouldn't directly harm life. However, we've neglected several factors. First, quasars emit heavily in ultraviolet and X-rays. While visible light is mostly harmless, UV and X-rays damage biological molecules, including DNA. If the galactic center quasar emitted 10% of its luminosity as X-rays, X-ray is approximately equal to 2 times 10 to the power of negative 6 ergs cm squared s. Earth's atmosphere absorbs X-rays, so surface life would be protected. But satellites, spacecraft, and astronauts in space would face increased radiation, perhaps manageable with shielding, but concerning nonetheless. Second, quasars ionize gas. A galactic center quasar would ionize the interstellar medium throughout the Milky Way, potentially affecting star formation and cosmic ray propagation. This wouldn't directly harm Earth, but over millions of years, altered galactic conditions might indirectly influence Earth's environment. Third, jets are a wild card. If the galactic center produced relativistic jets, their orientation matters. If aimed away from Earth, they'd pose no direct threat. If aimed toward Earth, the situation worsens dramatically. Relativistic beaming could concentrate radiation, increasing flux by factors of 10 to 100. Additionally, jets accelerate particles to ultra-high energies. If a jet pointed at Earth, we'd be bathed in cosmic rays, high-energy protons and nuclei that penetrate the atmosphere, increasing surface radiation levels, potentially damaging the ozone layer, and increasing mutation rates. The probability of a jet precisely aligned with Earth is low. Jets are narrow, subtending small solid angles. But in a galaxy hosting a quasar, many stars and planets orbit the center. Some inevitably lie along or near the jet axis, facing its full fury. For planets within a quasar's host galaxy, particularly those near the galactic center, conditions are extreme. Within a few kiloparsecs, thousands of light-years of an active quasar, radiation flux can rival or exceed that from the host star. Ultraviolet and X-ray radiation strips planetary atmospheres, breaks apart molecules, and sterilizes surfaces. Planets in this region might lose their atmospheres entirely over millions of years, becoming barren rocks. Life, if it existed, would need to retreat underground or underwater, shielded by rock or liquid from the quasar's radiation. Surface life would be impossible. Photosynthesis, dependent on visible light without excessive UV, might be disrupted. The intense radiation could drive chemistry in unexpected ways, perhaps creating exotic prebiotic molecules, but also destroying complex organics. Even planets far from the center feel effects. Quasar-driven winds and jets expel gas from galaxies, stripping material from molecular clouds where stars and planets form. Regions of galaxies affected by quasar feedback might see suppressed star formation, fewer planets, and altered chemical compositions. Another danger: variability and flares. Quasars vary in brightness, sometimes dramatically, over timescales from days to years. If a quasar suddenly brightened, perhaps from a star or gas cloud falling into the black hole, radiation could spike. A planet accustomed to certain radiation levels might suddenly face a 100-fold increase, with catastrophic consequences for climate and life. Consider also the long-term view. Quasars are transient. A galaxy's quasar phase might last 100 million years, then shut down as gas is exhausted. Planets in such galaxies experience epochs of intense radiation, interspersed with quieter periods. Life might adapt during quiescent periods, only to face extinction when the quasar reignites during a merger or gas infall event. From an astrobiological perspective, quasars present a paradox. Their radiation could sterilize large regions, rendering them hostile to life. But quasar-driven processes also enrich galaxies with heavy elements via supernovae from triggered star formation, create complex chemistry through ionization, and regulate galaxy evolution in ways that might ultimately favor life by preventing runaway star formation or cooling catastrophes. Some researchers speculate that quasars could be both harmful and beneficial. In the early universe, quasars might have helped end the cosmic dark ages, reionizing hydrogen and allowing light to travel freely. This reionization, while sterilizing any early life, set the stage for later structure formation and the emergence of habitable galaxies. For Earth specifically, the risk from quasars is effectively zero. No nearby galaxy will host a bright quasar soon. Quasars require gas-rich conditions and mergers, rare in the local universe. The Milky Way's central black hole is dormant and unlikely to ignite as a major quasar. Even if it did, our distance provides ample protection. Andromeda, the nearest large galaxy, hosts a supermassive black hole similar to Sagittarius A*. In about 4 billion years, Andromeda and the Milky Way will collide, potentially funneling gas to both central black holes and triggering AGN activity. But by then, the Sun will be nearing the end of its main sequence life, swelling into a red giant and rendering Earth uninhabitable anyway. The quasar threat, if it materializes, will arrive long after Earth's biosphere has naturally ended. In summary, quasars are dangerous, but danger is localized to their host galaxies, and within those galaxies, primarily to regions within a few thousand light-years of the core. For distant observers like us, quasars are fascinating but harmless, their light weakened by billions of light-years of space into faint glimmers, scientific treasures, not existential threats. Quasars aren't isolated phenomena, they're integral to galaxy evolution, influencing and being influenced by the galaxies hosting them. Understanding this interplay illuminates cosmic history and structure. The relationship between supermassive black holes and galaxies is intimate. Observations reveal tight correlations. Black hole mass correlates with the stellar velocity dispersion of the host galaxy's bulge, the M-sigma relation, and with bulge mass, and with galaxy luminosity. These correlations suggest that black holes and galaxies co-evolve not independently, but through feedback mechanisms. The M-sigma relation discovered in the early 2000s shows that black hole mass is proportional to stellar velocity dispersion, sigma to the fourth or fifth power. BH is proportional to sigma to the power of 4 or sigma to the power of 5. This is remarkable. Black hole masses span 7 orders of magnitude, 10 to the power of 6 to 10 to the power of 10 solar masses, yet they correlate tightly with bulge properties. The bulge is much larger than the black hole's sphere of influence, typically a few parsecs. So how do they know about each other? The answer is feedback. When a quasar is active, its radiation and jets affect the entire galaxy. AGN feedback comes in 2 modes: quasar mode or radiative mode during bright quasar phases, and radio mode during lower accretion rates with powerful jets. Both modes inject energy into the galaxy and beyond, regulating star formation and black hole growth. During quasar mode, intense radiation pressure drives winds, outflows of gas, moving at thousands of kilometers per second. These winds sweep through the galaxy, compressing or expelling gas. If expelled, gas can't form stars or feed the black hole, quenching both star formation and black hole growth. Observations detect such outflows in many quasars with speeds up to 0. 1c and mass outflow rates exceeding the star formation rate, indicating that quasars are actively removing the fuel supply. Radio mode feedback operates through jets. Jets inflate cavities in the surrounding medium, heating gas and preventing it from cooling and forming stars. This mode is particularly important in massive elliptical galaxies and galaxy clusters, where cooling flows would otherwise lead to excessive star formation. Simulations of galaxy formation that include AGN feedback reproduce observed galaxy properties much better than those without it. Without feedback, simulated galaxies form too many stars too quickly, becoming overly massive and blue. AGN feedback suppresses this overcooling, producing galaxies matching observations, massive red ellipticals with old stellar populations and little ongoing star formation. Quasars also affect the intergalactic medium, IGM. Their ionizing radiation escapes the host galaxy, ionizing hydrogen in the IGM over vast scales. In the early universe, the combined radiation from quasars and young stars reionized the universe, transforming neutral hydrogen filling space after recombination. 380,000 years post-Big Bang, back into ionized plasma. Quasars, with their intense UV output, contributed significantly, especially in ionizing helium, which requires higher energy photons than hydrogen. Evidence for quasars' role in reionization includes the Gunn-Peterson trough absorption in quasar spectra bluewood of the Lyman alpha line, indicating neutral hydrogen along the line of sight. At redshifts Z is greater than 6, strong absorption appears, suggesting the universe was significantly neutral. By Z to 5.5, the trough disappears, indicating reionization was largely complete. Quasars observed at Z is greater than 6 show ionized bubbles around them, regions cleared of neutral hydrogen by the quasar's radiation. Quasars inject heavy elements into the IGM. Jets and winds carry metal-enriched gas from supernovae in the host galaxy, far beyond the galaxy, enriching intergalactic space. Observations detect metals in the IGM, and AGN-driven outflows are a likely source. The cosmic evolution of quasars parallels galaxy evolution. Quasar activity peaked when the universe was 2 to 3 billion years old, redshift Z to 2 to 3, coinciding with the era of peak star formation. Early galaxies were gas-rich, fueling both star formation and black hole growth. As gas was consumed, expelled, or locked into stars, both star formation and quasar activity declined. Today, the universe is in a quiescent phase. Star formation and quasar activity are much reduced compared to the peak epoch. Why did quasar activity decline? Several factors contribute. Gas was converted into stars, reducing the fuel available for black holes. Supernovae and quasar feedback expelled gas from galaxies. Galaxies evolved from gas-rich spirals and irregulars to gas-poor ellipticals. Mergers, major drivers of quasar activity, became less frequent as structure formation slowed. Quasars today are rare. The space density of bright quasars is about 1,000 times lower than at Z to 2. Most nearby massive galaxies have supermassive black holes, but these black holes are mostly dormant or have low accretion rates, producing weak AGN rather than quasars. This evolution implies that most galaxies went through a quasar phase. If quasars are triggered by mergers, and mergers were common in the early universe, then most massive galaxies experienced one or more quasar episodes. The Milky Way likely hosted a quasar billions of years ago, when it was younger and gas-rich. Evidence for past quasar activity in the Milky Way includes the Fermi bubble's enormous structures of high-energy gas extending 25,000 light-years above and below the galactic plane. Discovered by the Fermi Gamma Ray Space Telescope, these bubbles might be remnants of a past AGN outburst from Sagittarius A*, inflated by jets or radiation pressure millions of years ago. If so, the Milky Way was once more active, though not necessarily a full quasar. Quasars also influence large-scale structure. During their active phases, they deposit energy into intergalactic space, affecting the temperature and density of gas, influencing where and when galaxies form. AGN, clustering, the tendency of AGN to reside in overdense regions, suggests they trace large-scale structure, with environment playing a role in triggering activity. Galaxy mergers, while key triggers, aren't the only path. Secular processes, bar-driven inflows, minor mergers, cold mode accretion, gas flowing along cosmic filaments, can also fuel black holes. The relative importance of these mechanisms varies with cosmic time, galaxy mass, and environment. An intriguing question: do quasars regulate their own growth? As black holes grow, their luminosity increases. Eventually, radiation pressure and feedback become so strong that they halt further accretion. This self-regulation might explain the M-sigma relation. Black holes grow until their feedback balances inflows, establishing a set of equilibrium mass determined by galaxy properties. The interplay between quasars and galaxies is a two-way street. Galaxies provide the environment, gas, stars, dark matter that enables black hole growth. Black holes, through quasars and AGN, regulate galaxy evolution, preventing overcooling, quenching star formation, enriching the IGM, and shaping galaxy morphology. This feedback loop is fundamental to understanding why galaxies look the way they do and why the universe evolved from a hot, dense state to the structured cosmos we observe. Quasars, far from being exotic oddities, are key players in cosmic history, architects of structure, regulators of star formation, and markers of the universe's evolution from youth to maturity. Quasars, despite their distance and extreme nature, are among the most studied astronomical objects. Advances in telescopes and techniques have enabled detailed observations across the electromagnetic spectrum, revealing quasar properties and testing theories. Optical observations dominate historically. Early quasar discoveries came from optical telescopes identifying star-like objects with unusual spectra and high redshifts. Optical spectroscopy remains crucial. Splitting quasar light into spectra reveals emission lines, hydrogen, carbon, magnesium, oxygen, that indicate the quasar's redshift, composition, ionization state, and kinematics. The broad emission lines in quasar spectra are distinctive. Hydrogen-Balmer lines, H-alpha, and forbidden lines like OIIE appear broadened by thousands of kilometers per second, Doppler broadening from gas orbiting the black hole at high velocities. Measuring line widths and luminosities allows estimating black hole mass via the virial method, which assumes gravitational equilibrium. MBH is proportional to R times V squared, where R is the broadline region radius estimated from luminosity via reverberation mapping, and V is the gas velocity from line width. Reverberation mapping is a powerful technique. By monitoring how quasar luminosity changes and observing the delayed response in emission lines, astronomers measure the light travel time across the BLR, providing R. Combining this with velocity gives black hole mass. Reverberation mapping has been applied to hundreds of AGN, mapping black hole masses from millions to billions of solar masses. Radio observations reveal quasars' radio properties. Radio-loud quasars, constituting about 10% of all quasars, emit strongly in radio wavelengths from synchrotron radiation in jets. Radio interferometry, using arrays like the Very Large Array, VLA, or the Atacama Large Millimeter Array, provides high-resolution images of jets, showing their structure, collimated beams, hot spots where jets terminate, lobes of emission extending far beyond the host galaxy. Some quasars show superluminal motion jet components appearing to move faster than light across the sky. This is an illusion caused by relativistic beaming. Material moving near light speed toward us appears to traverse angular distance faster than light due to projection effects. Superluminal motion confirms jets move at relativistic speeds. X-ray observations probe the innermost regions. X-rays originate from the hot corona above the accretion disk and from the disk itself. X-ray spectroscopy reveals features like the iron K-alpha line, a fluorescent emission line at 6.4 keV produced when X-rays strike iron in the disk. The line's shape, broadened and skewed, reveals relativistic effects near the black hole, gravitational redshift, Doppler shifts, and light bending. Fitting the line profile provides insight into the disk's structure, black hole spin, and space-time geometry. X-ray variability studies show that quasars flicker on timescales from hours to years. Short timescale variability implies small emission regions, consistent with accretion disks. Longer variability might reflect changes in accretion rate or disk instabilities. Infrared observations trace dust. The dusty torus surrounding the central engine absorbs UV and optical radiation, re-emitting it as infrared. Infrared surveys, like those by the Wide Field Infrared Survey Explorer, detect dust-obscured quasars, invisible in optical wavelengths. Studying these reveals hidden AGN populations, important for understanding the full census of quasar activity. Ultraviolet observations capture the disk's peak emission. The Hubble Space Telescope's UV spectrographs have observed hundreds of quasars, measuring UV luminosity and spectra. UV emission traces the accretion rate as hotter, more luminous disks emit more UV. Gamma-ray observations focus on blazars quasars with jets aimed at Earth. The Fermi Gamma-ray Space Telescope detects blazars emitting up to 10 GeV or higher. Gamma rays come from inverse Compton scattering in jets, where electrons boost photon energies to extreme levels. Gamma ray variability is dramatic, with some blazars flaring on timescales of hours, indicating compact emission regions moving relativistically down the jet. Multi-wavelength observations are essential. A quasar emitting across radio, infrared, optical, UV, X-ray, and gamma-ray bands presents a puzzle that no single wavelength solves. Simultaneous or coordinated observations across wavelengths reveal how different components disk, corona, BLR, NLR, jet, torus contribute to the total energy output and respond to variations. Gravitational lensing offers a unique tool. When a massive galaxy lies between Earth and a distant quasar, the galaxy's gravity bends light, creating multiple images of the quasar. This gravitational lensing magnifies and brightens the quasar, allowing study of fainter or more distant objects. Lensed quasars also enable measuring the Hubble constant and testing cosmological models, as time delays between images caused by different light path lengths depend on the universe's expansion rate. Spectroscopy of quasar absorption lines provides information about intervening material. Light from a distant quasar passes through intergalactic gas, which absorbs specific wavelengths, creating absorption lines in the spectrum. The Lyman alpha forest, multitudes of hydrogen absorption lines at different redshifts, maps the distribution of neutral hydrogen along the line of sight, tracing structure formation and the IgM's evolution. Future observatories will push boundaries further. The James Webb Space Telescope, with its infrared sensitivity, will detect the most distant quasars, probing the universe's first billion years and the earliest supermassive black holes. The Extremely Large Telescope, ELT, and 30-meter telescope, TMT, with enormous mirrors, will provide unprecedented resolution and sensitivity, imaging quasar host galaxies and studying accretion physics in detail. The Square Kilometre Array, SKA, a next-generation radio telescope, will survey radio-loud quasars with incredible depth and resolution, mapping jets and understanding their impact on galaxies. The Athena X-ray Observatory will study the hot gas around quasars, probing feedback and the interplay between black holes and their environments. Gravitational wave detectors like LISA, Laser Interferometer, Space Antenna, will detect supermassive black hole mergers, offering insights into how quasars' central engines form and evolve. When two supermassive black holes spiral together, they emit gravitational waves detectable across the universe, providing a new window into quasar phenomena. Observations have transformed quasars from mysterious quasi-stellar objects to well-understood systems where gravity, magnetism, and accretion combine to produce nature's most extreme displays. Yet, mysteries remain how supermassive black holes formed so early, the precise mechanisms driving jets, the detailed physics of accretion disks under extreme conditions. Future observations will continue unraveling these mysteries, deepening our understanding of the cosmos's most powerful objects. Quasars are not eternal. They're transient phases in a galaxy's life, lasting millions to hundreds of millions of years short, compared to the 13.8 billion year age of the universe. What will become of quasars, and what role will they play in the universe's distant future? As discussed, quasar activity peaked when the universe was young. Today, quasars are rare and their numbers continue to decline. The universe is settling into a quieter state, with galaxies aging, gas supplies dwindling, and mergers becoming infrequent. In the far future, quasar activity will become even rarer. But will quasars disappear entirely? Not necessarily. Future galaxy mergers will occasionally funnel gas to central black holes, reigniting quasar activity. The Milky Way-Andromeda merger, occurring in roughly 4 billion years, might trigger AGN activity in both galaxies' black holes, potentially creating quasars, though likely not as luminous as those in the early universe, given lower gas content. Over tens of billions of years, galaxies will continue merging, building larger galaxies with larger central black holes. Eventually, these mergers might create ultramassive black holes exceeding 10 billion solar masses, hosting the most luminous quasars the universe has ever seen, though such events will be exceedingly rare. Galaxy clusters, which grow through mergers of member galaxies, will eventually contain a single giant elliptical galaxy formed from merging all cluster members. The central black hole, formed from merging all member black holes, could reach tens or hundreds of billions of solar masses. If fresh gas somehow reaches this black hole, it could power a quasar of unprecedented luminosity, though by then the universe will be so old and diffuse that gas supplies will be minimal. Another consideration is Hawking radiation. Black holes, according to quantum theory, emit faint thermal radiation, Hawking radiation causing them to lose mass slowly. The evaporation timescale is proportional to black hole mass cubed. So supermassive black holes will take an unimaginably long time to evaporate, far longer than the current age of the universe. A billion solar mass black hole will take roughly 10 to the power of 100 years to evaporate, vastly longer than the universe's current 10 to the power of 10 year age. But in the ultimate far future, trillions of years hence, supermassive black holes will eventually evaporate, disappearing in a final burst of radiation. By then, the universe will be dark, cold, and nearly empty. Stars will have burned out, galaxies dispersed, and even black holes will vanish. Quasars, creatures of an active, dynamic universe, will be distant memories encoded in the photons they emitted eons ago, traveling through an empty cosmos forever. In the nearer term, next billions of years, quasars will continue playing a role, albeit diminished. Observations of the local universe will catch occasional quasars igniting in merging or disturbed galaxies. Radio-loud AGN will continue blowing bubbles in galaxy clusters, heating intergalactic gas. Isolated quasars might flicker into existence when a star wanders too close to a supermassive black hole, torn apart and accreted in a tidal disruption event, creating a brief burst of quasar-like luminosity. Tidal disruption events, TDEs, are transient flares occurring when a star passes within the tidal radius of a supermassive black hole, where tidal forces exceed the star's self-gravity, ripping it apart. Half the star's material gets flung away, the other half accretes, producing a flare lasting months to years, with luminosities approaching AGN levels. TDEs provide snapshots of accretion physics and might be common in otherwise dormant galaxies. Human exploration, if it survives billions of years and spreads across the cosmos, might one day observe quasars up close or their remnants. Visiting a galaxy that once hosted a quasar could reveal evidence of past activity, fossil radiolobes, remnant jets, metal-enriched gas, and the quiescent supermassive black hole itself, massive and dark, surrounded by stars and planets shaped by its violent past. There's speculation that advanced civilizations might harness black holes for energy. The Penrose process allows extracting rotational energy from a spinning black hole. By dropping matter into the ergosphere, a region outside the event horizon where space-time is dragged along, one can extract energy and use it for propulsion or power. A sufficiently advanced civilization might build a black hole engine, extracting energy comparable to quasar luminosities but controlled and directed for their purposes. If such civilizations exist, they might create artificial quasars or quasar-like objects, beacons visible across the universe. Searching for such technosignatures is speculative but intriguing. Could some quasars actually be engineered objects? Almost certainly not. Quasar properties match natural accretion physics too well, but the idea illustrates how quasars fire the imagination. Quasars also serve as cosmological tools. Because they're so distant, quasars probe the universe's expansion history. Measuring quasars' redshifts and distances via luminosity or other methods contributes to understanding dark energy and the universe's fate. Quasar clustering and correlations with structure inform models of galaxy formation. Quasars are also laboratories for extreme physics. Near a quasar's black hole, space-time is curved sharply, matter moves relativistically, magnetic fields reach extreme strengths, and temperatures exceed billions of degrees. Studying these environments tests general relativity, quantum field theory in curved space-time, and plasma physics under conditions impossible to replicate on Earth. Ultimately, quasars' legacy is written in the galaxies they shaped. Every massive galaxy with a supermassive black hole likely hosted a quasar long ago. The M-sigma relation, the red and dead elliptical galaxies, the metal-enriched IgM all bear the imprint of quasar activity. Quasars were sculptors of the cosmos, their violent energy forging structure and regulating star formation across billions of years. As we drift towards sleep, imagine the future universe. Dark galaxies orbiting larger clusters, occasional bursts of activity as stars fall into black holes, and in the deep background, faint echoes of ancient quasars whose light has traveled for eons. These monuments to energy and violence remind us that the universe, though vast and often quiet, is also dynamic, capable of producing phenomena that challenge our understanding and inspire our curiosity. We've journeyed through the universe's most extreme objects, quasars, powered by supermassive black holes, shining with the light of trillions of suns, reshaping galaxies with radiation and jets. We've learned what they are, how they form, the colossal energies they wield, and the dangers they pose. Quasars are monuments to nature's power, proof that gravity, when given enough mass and fuel, can create engines of unimaginable energy. They're not supernatural or magical, they're physics, but physics at extremes we struggle to comprehend. For humanity, quasars present no direct threat. Distance shields us billions of light-years separate Earth from the nearest quasars. Even if one ignited nearby, the radiation would be manageable at our distance. Quasars are cosmic hazards localized to their host galaxies, particularly regions near galactic centers. For civilizations unfortunate enough to live in quasar-host galaxies during active phases, survival would require retreating to galactic outskirts or even fleeing entirely. But quasars are more than dangers, they're teachers. Studying them illuminates black hole physics, accretion, jet formation, galaxy evolution, and the universe's history. Quasars mark cosmic eras, their abundance peaking when the universe was young and gas-rich, declining as galaxies matured. They also remind us of our place. The universe contains phenomena vastly more energetic and dangerous than anything on Earth. Our planet, orbiting a calm star in a quiet galaxy, is a sanctuary. We exist in a cosmic oasis, far from the violent centers where quasars blaze. Yet we're connected. The atoms in our bodies, forged in stars, were shaped by processes influenced by quasars. The metals in our blood, the carbon in our cells distributed through galaxies by supernovae and AGN-driven winds, link us to quasars' legacy. We're children of a universe sculptured by these cosmic monsters. As technology advances, we'll continue studying quasars, perhaps one day directly imaging the shadow of a supermassive black hole, as we did with M87 and Sagittarius A*, observing accretion disks and watching jets launch. Each observation deepens understanding and reminds us of the wonders awaiting discovery. Quasars embody the universe's duality, beautiful and terrifying, creative and destructive. They regulate galaxy formation, preventing overcooling and maintaining cosmic balance. Without quasars and AGN feedback, the universe might be overpopulated with massive, star-forming galaxies, consuming gas too quickly and leaving a cosmos barren of later structure. Quasars, by quenching star formation, paradoxically enable the orderly evolution that led to galaxies like ours, stars like the Sun, and planets like Earth. In contemplating quasars, we confront limits of distance, of energy, of understanding. They push boundaries of physics and imagination, challenging us to think bigger, to accept that the universe operates at scales dwarfing human experience. So tonight, as you drift towards sleep, think of quasars blazing across the cosmos, distant beacons marking the universe's most energetic sites, reminders that beyond our quiet corner, space harbors wonders and dangers beyond imagining. They've been shining for billions of years, their light traveling through expanding space, some photons arriving at Earth tonight, captured by telescopes, studied by astronomers, revealing secrets of the distant universe. Rest well, knowing that while quasars are the universe's most dangerous objects, they're also far away, their fury contained by the vastness of space. We're safe here, on our small world, protected by distance and the calm stability of our galaxy. Tomorrow, the sun will rise, gentle and steady, a reminder that we live in a peaceful region of a dynamic cosmos. Sweet dreams, fellow traveler. May your rest be as deep as the universe is vast, as peaceful as the space between galaxies, and as wondrous as the quasars that once blazed in the young universe, forging the structure that ultimately allowed us to exist, to wonder, and to dream beneath the stars.